Okay, good morning. Excuse me. So we're continuing with Newton's laws. We'll do some problems with the inclined planes and pulleys, and maybe we'll even touch on some circular motion so you can get a jump on that this weekend, and we'll do more next week with circular motion. So I've got a worksheet here that will help you maybe with some directions of forces and free body diagrams. But I think you can try those at home, and if you have any issues, let me know. The answers are snuck them in there at the bottom. So when you do them, you have some answers, but they're kind of hidden. So you can try to ignore those until you've come up with your own answers. All right, so this is the sheet that we were doing last time. We did the first part here, number 1, and came up with the motion diagram. Something like that, right? And so maybe you had a chance to go and look at those and try some of these others. So let's go through and do a couple of these. In this number 2, it says draw the normal force to the appropriate length. So somebody's pushing a box across the floor. We can see that there's a kinetic friction force. We can see that there's a pushing force that's not only pushing it to the right, but it's also pushing down a little bit on it. And then there's force of gravity here. So go ahead and draw that in if you haven't done it yet. So how long, what's the value of the normal force? $300 newtons. Because we know we have 200 here, and if we break P up into a vertical and a horizontal, we have another 100 here. So we add those up, and we know we have to have 300 in this direction. Okay. And what's the motion diagram look like? Is this object moving at constant speed as it goes across the floor? Is it speeding up? Is it slowing down? What's it doing? So we want to break up P into its components because all the other vectors are in that coordinate system, right? We want to pick, usually we pick the direction that the object would be accelerating, right? So along the incline is one of our directions, and then perpendicular to that is the other direction. Now we can compare things, right? Once we break P up into its components, then we can compare vertical forces and horizontal forces. So this object is accelerating to the right because the force to the right is 200 newtons, but the force to the left is only 150. So it's going to speed up a little. I'll start out a little slower. Okay. Okay, ready for number 3? So here we've got the motion diagram is given there next to the wall. You're going to fill in what's missing in the force diagram, free body diagram. Yeah, the crate is sliding down the incline. So the person is pushing it into the wall and up a little bit. And the crate is sliding down the wall. So how does a surface interact with something? Through a normal force and through a friction force. The normal force is perpendicular to the surface, and the friction force is parallel to the surface. So in this case, the normal force points this way. Now I haven't thought about the length yet. I will in a minute. Normal force points to the left, and the friction force is going to point up. As the box slides down, the friction force will go up. So now what are the lengths for these things? So is there acceleration is the question. Did you look at the motion diagram? The object's moving with constant velocity as it slides down. So there's zero acceleration. So we have to balance all these to zero, right? So our P, we can break P up into a P sub X and a P sub Y. And we know that there's no acceleration. So the two forces in the upward direction have to equal the weight down. So our friction has to be there, right? What is that? 100? And our normal force has to balance the horizontal force in the other direction, 200. Question was, if there's no P pushing the box into the wall, what happens to the normal force? Then the normal force goes to zero, right? The normal force goes to zero. Then the only force acting on this box is gravity, right? If there's no pushing force pushing it into the wall, then the only force acting on it would be gravity. Okay. So we're saying this thing has no acceleration, right? So the forces to the left equal the forces to the right, and the upward forces, which is the sum of those two, equal the force in the downward direction. Okay. So these are, I think these are quite helpful. Should we do one more? There are three, so that's one of the sheets. Here's the second one. And there's a third one also on the Canvas site under modules, if you think they're helpful. This one's on an incline, the last one here. So it'll help you think about what's going on along an incline. I think I'm going to move along. So those are there for you. Let me know if you want to go over them some more. I think they're very helpful. So what we want to do now, let's do a problem that's a little more interesting than the one we did last time with the box on an incline. Pulling a box up an incline with a rope. So our picture would look something like this. And we're going to make this a little more complicated. We're going to have our rope at an angle. So this angle is theta, where the incline makes an angle theta with the horizontal theta. And then we're pulling, and the rope is going to make an angle phi with the surface of the incline. And it's moving up at this instant. It has some velocity upward. So if we were given the coefficient of kinetic friction, the mass, the angles, and the pulling force, then we want to find the acceleration. Okay? So first thing I want to do is draw my system schema, just so you sort of see how I use this. Okay, I've got a rope. And a box. And the earth incline. And so because there's only really one end of the rope here, I'll show you how I deal with that. Something is reaching in and grabbing that rope, right? Maybe there's a hand or something. You. And so something, whenever I have just one end of a rope in a system or a hand kind of reaching in, I always draw it as an external force reaching into the system. And then I know I have to account for that somehow, what it's doing to the system. When we get to energy, you'll understand that a little bit more. So the rope is touching the box, right? There's some kind of a contact force between the rope and the box. And there's the box is touching the incline. And so there's a contact force there. And we always split that contact force into two forces, right? A normal force and a friction force. So I like to draw it like this. I like to draw it like a double arrow. So I know that there's two. There's one force that's represented by this side. That's maybe a normal force. And there's one that's represented by this side. That's a friction force. And when I count up in my free body diagram, I get 1, 2, 3, and then there's going to be one more over here because there's the force of gravity, the non-contact force of gravity. 1, 2, 3. So I should have 4 forces in my free body diagram for my box. Okay? So that's my system schema, and you'll see why that's helpful when we get to energy. So let's draw free body diagrams for the box. What should we do? Let's just do the box. I was going to have you do the earth also, but let's just do the box and move on. So how would you draw the free body diagram for the box? I do the double-sided arrow because the contact between the box and the earth, we always break that up into two vectors, right? One is the normal force and one is the friction force. So anytime I have surfaces interacting that have the two that I'm going to represent as two things in my free body diagram, I draw the double arrow like that to remind me that there's going to be two forces in my free body diagram for that single interaction, right? The box is interacting with the surface. It's really one interaction. But instead of saying, right, if I have a box moving this way on a surface, I could say the surface is doing this, right? I could say that. And that would be sort of a single arrow here between these two, between the box and the earth. But we normally don't do that. We normally write it like this. We normally write it as a normal force. That's an N. And a friction force. That's how we normally write it. But really, you could think of it as a single interaction. The box and the surface are interacting, and this is the result, right? We just happen to break that up into a normal force and a friction force. Since we always do that, I just draw it as two to remind me that there's going to be two forces in my free body diagram that represent that single interaction with the surface. Okay, so my surface is doing this, right? Sometimes it's convenient to sketch where the surface is. All right, so what's happening here? The box, what's touching the box? The rope. And the rope is pulling up at an angle. So we can draw a force in here that represents the tension in the rope. And this is some angle phi with respect to the surface, the inclined plane. What else is touching the box? The surface. And the surface we always break up usually, right, into two forces, a normal force, normal perpendicular to the surface, and a friction force, and in this case it's kinetic friction because it's sliding up the incline, right? And what can reach in from a distance? Gravity, F sub g and that points toward the center of the Earth. Now, what's convenient is to take this one step farther. This is actually a correct free body diagram. I could stop here, but usually we want to find a coordinate system that works for the geometry, for the situation we're in. In this case, we've got a box moving up and down an incline, so we want to pick that as one of our directions. So we want to orient our coordinate system with the incline and perpendicular to the incline. So if we do that, we could redraw this. And we would have a normal force is already in that coordinate system, right? Friction force is already in that coordinate system. But we could split up our tension. So we have a tension, what do you want to call it? X and Y, or parallel and perpendicular? Let's call it parallel and perpendicular. So this will be our parallel direction, parallel to the motion, right? Parallel to the motion. And this will be our perpendicular direction. So this would be T parallel, and this would be T perpendicular. And we would break up our gravity, F sub g perpendicular, F sub g parallel. Oh, I told you, yeah, good question about kinetic friction. You can't figure out sometimes what direction the friction is unless you're told what direction the object is moving, okay? And I think I told you here, yeah. I snuck it in there, maybe I didn't say anything. The box, at this instant, the box is moving up the incline. Maybe I'll write it over here too. Yeah, good question. You have to be told what direction it's moving unless it's really obvious. Like, for example, if we had this situation, and we said V initial was 0. So if we release this from rest, there's only one way it can go, right? It's not going to start moving. This isn't magically going to move this way if we release it from rest. It's got to go the other way, right? So that's kind of an obvious situation. But if it's not released from rest, you don't know which way it's going. Maybe I gave this thing a push and it has some initial velocity in this direction. And as it moves, it's going to slow down, come to rest, and then start going back in the other direction, right? Or maybe it's already moving to the right. We don't know, right? You don't have enough information. So usually you'd have to be told something about the initial velocity, unless it's, like I said, it's obvious you're releasing it from rest and it can only go one way. Yeah. Good. Okay, so now I've got a nice free body diagram there. Let's go through and figure out what each of these things are. So force of gravity, that's just mg, right? Force of gravity perpendicular to the direction of motion is going to be what? mg cos. Good. Cosine theta. Force of gravity parallel mg sine theta. T, tension in that rope parallel to the surface is going to be T cosine phi, and the tension in the rope perpendicular is T sine phi. So those are all the components there that I have up above. And now what do? We say sum of the forces equals MA on this box, right? Sum of the forces equals MA. This is a vector equation. So what do? Normally we split that up into components. Parallel. And I'll say up the incline is my positive direction. And then we say sum of the forces perpendicular, MA perpendicular, and I'll say sort of up that way is my positive direction. Okay, so let's do the perpendicular direction first. Is the box going to jump up off the surface or fall through the surface? No, the box is always at the same level, right? Always sliding along the surface. So that means that there's no acceleration in that direction. A perpendicular is 0. It's always on the surface. It never jumps up off the surface or moves in that direction. So this direction, I'll call it, what are we calling it? Let's use red. This is this one, right? So I have 3 forces in that direction. A normal force and T perpendicular that are in my positive direction, right? Why are we doing this perpendicular direction? To find the normal force. So normal force and T perpendicular point in my positive direction. You can see those right there, right? And in my negative direction, I've got F sub G perpendicular. And those have to sum to 0. So why am I doing the perpendicular direction? To get the normal force. Why do I need the normal force? Because there's friction force over here in my equation, and I have to substitute in for that. Okay, so the normal force is going to be FG perpendicular minus T perpendicular. And what is that? That's mg cosine theta minus T sine phi. So now I know my normal force. I think all of that was given. You can see how normal force can get complicated, right? You don't want to get in the habit of thinking, oh, normal force just equals the weight of my object. Well, as soon as you go on an incline, it's not the weight, it's mg cosine theta. And then as soon as you have other things pulling or pushing on it, if you have a rope pulling out at an angle, the rope is holding up some of the weight of the object, so the surface doesn't have to push as hard on the object, right? The normal force is less. Think about what the rope is doing. In this case, the rope is pulling up. So the normal force has to be less because of that rope pulling up. So make sure you get your signs right. Think a little bit about what's happening. Okay, ready for the other direction? So now we're going to look at this direction. I'll use green here. We're going to look at this direction, and that would be this one. So I have two forces. I have two forces in the negative direction and one force in the positive direction. And I'm just going to call it A now. I know the only acceleration in my system is along the incline, so I'm just going to call it A. And I can plug in what I know. This is T times the cosine of phi. This is mu K times the normal force. And then I have mg sine theta, and that has to equal ma. So as soon as I plug n in there, I can solve for A. Okay. Okay, I think I want to touch on circular motion. We'll see how far we get. But this way you'll be able to start hitting it over the weekend, because our next exam is a week from today, right? So that's going to be all Newton's law stuff, which means problems with inclined planes, pulleys, and masses, right? Finding tensions and accelerations, things like that. But it also means circular motion. Circular motion problems are perfect example of Newton's law application. So let's take a look at that. So we have uniform circular motion. And that means that the speed is constant. So we have something moving in a circle. At first, it's moving over here, velocity v1. At some later time, it's over here, velocity v2. At some later time, it's over here, velocity v3, right? But if it's constant speed, the magnitudes are all the same, right? But what's the acceleration? Not zero, right? Not zero, because the direction is changing. Anytime velocity is changing, there's acceleration. And in this case, the velocity is changing. The magnitude isn't, but the direction is, right? And velocity is a vector quantity. So if either one of those things changes, velocity changes. So let's take a look at the acceleration. If we did just a simple vector addition, if we took what is the acceleration, the average acceleration is going to be delta v over the time, right? That means it's v final minus v initial over the time. So if we're going from 1 to 2 here, v2 minus v1, what is the opposite of v1? It would be this vector right here. And what is the acceleration? The acceleration points this way. What if we did between 2 and 3? I'd have to add the opposite of V2 here. The opposite of V2. And then I'd get my acceleration. I'm running out of room there. Let me do it. So my acceleration would point like this. Where do all the accelerations point? Toward the center of the circle. Okay. We could do any two velocities. We would get the acceleration points toward the center of the circle. And we know it has to have this special value for circular motion. If something is moving in a circular path, there's a special value the acceleration has to have in the radial direction. It has to be v squared over r. And so we call that centripetal, right? Centripetal acceleration. That's toward the center of the circle. There has to be some force pulling in toward the center of the circle, causing the direction of the velocity to change, keeping the object moving in a circular path. And that's what this is, centripetal acceleration. Now, if the motion is not uniform, circular motion, if it's speeding up or slowing down, then what happens? Then we have an object moving, and it's moving in some direction here. So there has to be a component of the acceleration that's in this direction, right? We'll call that radial acceleration. That's causing the object to keep moving in a circle, right? There has to be some force pulling in on it. Well, if the speed is increasing, then there would also have to be a force in this direction, right? Causing the speed to increase, or an acceleration in that direction. The tangential acceleration. So the total acceleration would be in this direction, right? But we kind of break it up and like to think about it as there's a tangential part that's causing the speed to increase, or if it was in the opposite direction, decrease. And there's a radial part that causes it to stay moving in a circular path. Let me write that out here. So this one, a tangential causes the object to speed up or slow down. And this one, a radial, changes the direction. Yes, radial and a centripetal are the same. What's it useful for? Anything moving in a circle. We'll get to some examples. Okay. Just go to the amusement park and think about all the amusement park rides that spin around. Okay, so let's do let's think about this for a second. Let's do, what do I want to do? I'm going to do, okay, so we've got some mass on a string and we're swinging it around in a vertical circle, right? So its motion forms a vertical plane and it's spinning like this or like this, however you want to visualize it. And so we've got our, if we're looking from the side, we've got our mass here. It's got some velocity at that instant, but it's moving in a circular path. It's doing that, right? And here's our string. Excuse me. And let's just have it moving in uniform. It's a little hard, but maybe we could get it to move in uniform circular motion. So that means the speed is constant. We'll just call it V. Okay, so if we're given the mass, m, the speed, v, and the radius, then we want to find the tension in the string. At the top and the bottom. It doesn't have to have constant speed for the exam. Question about is the exam only uniform circular motion? I'd say no, the speed could be changing. Okay, so let's draw a free body diagram. Let's do the bottom first. Draw a free body diagram for the object at the bottom there. Only one thing touching our object, the string. What can reach in from a distance? Gravity. And so there's our free body diagram. Now what do? We say Newton's law, right? Sum of the forces equals ma. And what I do, I always pick radially inward as my positive direction. I'll show you why later. So what direction is positive? In this case, up. Okay, so what do I know? Sum of the forces, up is positive. T points in my positive direction. Mg in the negative direction, so T minus mg. And what do I know about acceleration when something is moving in a circle? I know it has to have this special value, v squared over r. It is centripetal acceleration. So I can put in here v squared over r. So now this is why I always pick towards the center of the circle to be positive. V squared over r, if you're plugging numbers in there, it's always going to be positive, right? V squared and r, how you can't get a negative number, right? Those are always positive. But if I picked down as my positive direction, my acceleration points toward the center of the circle. I would have to remember to put a negative sign here, negative v squared over r, because it points in the negative direction. And I usually forget that. I'm just telling you how I am. Maybe you're better at these things than I am. So what I do, my workaround, is to just always pick toward the center of the circle to be positive. So I know my acceleration is going to be positive. And then I don't forget the minus sign. But you can pick any direction you want to be positive as long as you remember to get the signs right. My trick is it kind of makes it hard to get the signs wrong. If you pick radially inward as possible as positive, it makes it hard to get the signs wrong. Okay, so there's my equation, and I just solve for t. I'm given everything else, right? So t is mg plus mv squared over r. And what does that mean? It means what is the string doing when the object is at the bottom of the path? The string is not only holding up the weight of the object, it's also providing the force needed to change the direction of motion. So this tension in the string is quite large. It's holding up the weight of the object, plus providing the force necessary to keep the object moving in a circular path. By radially inward, I mean towards the center of the circular path of motion, towards the center of the circle that the object is moving on. Okay, now let's do it at the top. V squared over r, centripetal acceleration is for any circular path, for any circular motion. So if an object, this circular motion happens to be a vertical circle, but that doesn't always have to be. It could be a horizontal circle. It could be, I guess those are mainly, I guess could be in between. But yeah, it could be a horizontal circle, something, a car driving around a corner on a road. That's circular motion, right? Ah, okay. Question about centripetal force in free body diagrams. So centripetal force is not some new force we're learning about, okay? What did we learn about? We've got normal forces, we've got tensions, we've got friction forces, and whatever else we've got, gravitational force, right? We've got all these forces. We don't now have a new force. Centripetal force is not a new force. It's a special name we give to the net force in the radial direction when we know something is moving in a circular path, because we know what the acceleration is at that instant. It's v squared over r. So the net force has to be mv squared over r. So it should not show up in a free body diagram, right? Let's think about what causes centripetal force in this example. We've got a blob on a string swinging around, right? What's causing the centripetal force? Tension in the string, right? Tension in the string. Let's think about a car moving around a circular path here. What causes the centripetal force as the car rounds the turn on a horizontal, flat surface? Friction, static friction between the tire and the road, pushing in on the car, right? A force that we know about, static friction, right? What causes the centripetal force for a satellite going around the Earth? Gravity. There's a gravitational force. It's the only force acting on that satellite is gravity. That keeps it moving. If we could shut gravity off, what would happen to our satellite? It would all of a sudden start moving in a straight line, right? It would be out of here. But with gravity there pulling on it, the satellite keeps moving in an orbit, right? So gravity. So what should be in your free body diagrams? Nothing called F centripetal. All the other forces that we know about, gravity, tension, friction, normal forces, all those other forces should be in there. And then when you write your equation, the sum of all of those forces in the radial direction, that's what we, at the end, we say, oh, this is our centripetal force. Okay, good. So real quickly, at the top, free body diagram. Tension in the string, what else points down? mg, right? So we say sum of the forces has to be m acentripetal because we know this thing is moving in a circular path. We're going to pick towards the center of our circular path as the positive direction, right? Because that's downward. We're going to make down positive. And that means I have a positive mg and a positive tension and a positive v squared over r for my acceleration. And so my tension now is mg is mv squared over r minus mg. So the weight of the object is providing some of the force needed to keep the object moving in a circular path. And the string just has to provide what else is the extra that's needed to keep it moving in a circle. Okay? So if you think about, if you don't mind me taking one more minute, some of the forces in the radial direction. So if the net force in the radial direction is bigger than mv squared over r, then what happens to our object? It spirals in, okay? If the net force in the radial direction is equal to this magic value, mv squared over r, what happens to our object? Circular motion. And if, I'm running out of room here, if the net force in the radial direction is less than our special value, then what happens? Then it spirals out. Yes, yes. Okay, so that's where we'll stop today. Hopefully that gives you enough to think about for some simple problems over the weekend so you can kind of get started on things, and we'll continue next week. Remember, exam 2 a week from today. So I'm going to stop the recording, but I will stick around because we have our review session right now, right? All right, have a good weekend if I don't see you at the review.